All right, welcome everyone. Welcome to Controls. Happy to see you all this morning. Glad you're here with us. Today we're going to talk about block diagram reduction, but I did want to take a couple moments just to do some announcements. So we've got another homework coming up. So I've been seeing some of you all in office hours. As always, please feel free to reach out for additional office hours if you need them. I can almost always make that happen. But I will sometimes combine multiple people who are asking in an additional session. So it might be multiple people. Also, if at any time I've said that I'm available for office hours, but you come up and my office door is closed, it probably means there were too many people to fit in my office. So we went out to the lounge area on the second floor up here where there are whiteboards and a lot more seats. It's a lot more comfortable over there. So if I'm not in my office, but I said I'm available for office hours, that's where we're at, okay? We've got quiz 2 coming up. I believe that's next week, and another homework that same week. All right. Okie dokie. I also did just this morning, I finally got a chance to re-record lecture 3, which was one of the days that I failed at recording my lecture. So I will be uploading that hopefully today. It does take a couple of hours to upload. But after that is uploaded and after I upload today's lecture, which I am recording, we will be totally up to date. So Dr. Higgins' lecture YouTube playlist will be up to date after today, which is great because it means that you can rewatch any lecture that you choose in preparation for our first exam, which is not super soon, but is on the horizon, right? Okay, as I do most classes, I'd like to start out today by just taking a quick reminder of what we did last time we met. So last time we talked about the time response of second order systems. So remember, we spent 2 lectures on the time responsive systems. The first lecture, we just covered first order systems. Those had a pretty simple response. Last class, we talked about second order systems, which had quite a few different possible behaviors that were all determined by the nature of the poles of the transfer function for that system. Okay, so we say the behavior of these systems depends mostly on the types of poles in the transfer function of the system. Okay, and then we talked about a couple of time specification metrics. We talked about the rise time. We talked about the settling time, we talked about the peak time, and we talked about percent overshoot. Even more specifically, we analyzed just the natural response of these second order systems. When I say natural response, what is the other type of response we sometimes talk about? Forced response, right? So last class, we really only looked at just the system on its own without adding any annoying engineering input. So some engineer didn't come and kick this system, giving an impulse input or a step input or whatever it was. We just looked at the system on its own. Question, Jerry?
That'll usually correspond to the homogeneous and inhomogeneous solutions, or no?
Yes. Right. When you look at the system, you should be able to break it up into the natural terms and the forced terms, which does relate back to the homogeneous and non-homogeneous solutions. Okay, but remember in this class, we take a shortcut for solving those differential equations by taking the Laplace transform, solving for big X of S, and then taking the inverse Laplace transform. So we don't have to memorize anything about ease, we just look at our Laplace transform tables, okay? All right, and then, so I said, you guys told me that this is different than the forced response. So today, this is my plug for today, we're gonna start looking at what happens when we add a controller to these types of systems. Okay, so last class we did not look at forced systems or feedback loops. All right, so that's my teaser for today. Today we are going to start looking at these forced and feedback loop systems by taking a closer look at block diagrams. So we'll look at block diagrams and see how we can take what might start out as a pretty ugly block diagram of a really complicated system and write an equivalent system that is just one input, one transfer function, one output. So we're going to take a nasty block diagram and reduce it down to a more simplified form. And then that simplified form is what we can analyze using a lot of the same tools that we've already talked about for second order systems. Okay, so let's say, let's just review very quickly. In case you forgot what block diagrams are, we say control systems are frequently represented by a connection of multiple subsystems. Let's see what we mean by that. So we're used to seeing the most simple, like feed forward block diagram as an input, some system block. Here I'm drawing a massive system block. So we have some input, R of S, some output, maybe we'll call it D of S just to be special for today. And we've got some system block. So this is what we're used to seeing. But in all actuality, this big system might be made up of several subsystems. Okay, so we might draw that. I always choose too big of an eraser. We might draw that like this. Instead of going into this big block, we might have a subsystem followed by a subsystem followed by a subsystem. Okay, and then mathematically speaking, remind me, what goes in these system blocks? Transfer functions, yeah. And a transfer function, we said, is a really simple ratio of output over input. Okay, so let's say our input to this very first block is R of S. We call that a signal. The arrows are representative of signals, and the blocks are representative of systems. So we said if you took this class maybe a decade ago, it might be a different name. It might be called signals and systems instead of controls. So our first signal is R of S, and then let's give a name to this output signal here in the middle. Maybe we call it E of S, which means that the transfer function in between here should be E of S over R of S. So if I take that transfer function, E of S over R of S, what math describes what I do with that R of S coming in? I multiply it, right? I take that R of S, I multiply times the transfer function. You can think of it as canceling out the R of S's. I have an R of S on top and I have an R of S on bottom. And then once those cancel, all that's left is the numerator, which is the output, E of S. Okay, so I take R of S, I multiply it. Here, I get E of S. So let's say this next signal here is C of S. What would the transfer function for this next subsystem look like?
E of S over C of S over E of S. Whoops.
Yep, C of S. This signal here is C of S, so it needs to be C of S over E of S. All right, tell me about this last one. What does this last one look like? D of S over C of S. Okay, cool. I'm going to give us actually some more space here. All right, so I have this nice big complicated system. What if I wanted to reduce the math here. If I were to work through all of the math to get from R of S to D of S, it would be something like R of S times E of S over R of S equals E of S. And then I need to take that and I need to multiply it times C of S over E of S. And that equals C of S. And then multiply that times D of S over C of S. And that would give us D of S. What is a reduced way of getting the transfer function of everything within this larger system?
Just D of S over R of S?
Kind of. D of S over R of S. What would I need to do to get that?
Multiply times R of S.
Multiply each transfer function by each other?
Multiply all the transfer functions. All of the transfer functions multiply, right? So I have E of S over R of S times C of S over E of S times D of S over C of S. If we look at this carefully, our E's will cancel, our C's will cancel, and I'm left with D of S over R of S. Congratulations, you just reduced the cascade form of a block diagram. All right, so we kind of brute forced our way through that logic. Let's add a little bit more detail to what we just did and actually classify certain particular forms of block diagrams. So we reduced all the subsystems into a single transfer function by multiplying all the transfer functions together. All right, I've already covered this to some extent. Just a reminder, in block diagrams, subsystems are represented by blocks. Those blocks contain transfer functions. And the arrows that come into and out of those systems are called signals. Good. Every block has an entering and departing arrow called a signal. And the way that we get the output is by multiplying the input by the transfer function within the system. All right, so now we know how to deal with signals, we know how to deal with systems, but there are actually a couple of components that you've seen before when we drew our very first feedback loops. There are certain components to that have names that you don't know the names of quite yet. So let's look at other components. If I were to draw something that looks like this, where I take a single input and I want to take copies of it to several different branches. And I have it look like this. This is what we call a pick-off point. Okay, so if you see one arrow get split into multiple arrows, we call that a pick-off point. And it's just the same as taking a copy of that signal and sending it to multiple branches. The next thing that you have actually seen before is this thing. And I've used words to describe this before. What do I call this? A summation junction, right? So some of the signals, they might be positive, in which case we sum the signals. But we could also have negative inputs as well. We still call it a summation junction. So if I, for instance, have an input R1 of S, R2 of S, and R3 of S, my output of this summation junction is equal to what?
1 plus 2 minus 3.
1 plus 2 minus 3. So R1 is positive, R2 is positive, and R3 is negative. Okay, now let's relate this to our simple standard feedback form. You've seen both of these things within the feedback loop. So our standard feedback loop without input and output transducers, we'll leave those out for now. We've already seen a summation junction. This is a summation junction. It comes into a system that we call our control. And I'm going to give this a transfer function big H of S. This usually goes into a plant. We usually give this a G of S, which creates an output C of S. We then have a pickoff point that goes back as feedback. All right, I can also label some other signals here. I've labeled the input signal and the output signal. The output signal goes as feedback off of a pickoff point. We can also, this one is a canonical signal. What do we call this one?
Error.
Error, yeah, because it's our desired minus our actual. So we usually call this E of S, or our error signal. And then what do we call what comes out of the control block? Doesn't really matter what letter you use, but we call it the same thing.
The actuating?
We can call it the actuating signal or the control signal, whatever it is. Sometimes it goes into an actuator, sometimes it goes into something slightly different, but we always call it the control signal, and I'll give it the value D of S here. Okay, so you've seen these components, but now you know that this is called a summation junction. Ooh, gosh. And this is called a pickoff point. All right. So what you're seeing here is a standard feedback form. This is one of 3 canonical forms that we will learn today how to reduce. So we have 3 canonical forms of block diagrams. The first, which you actually just saw in the very introduction of this lecture, is called the cascade form. I'm going to try to keep everything up on here. So cascade form is where one system goes into another system, goes into another system. Okay, we already talked about how to reduce this. How do we reduce this form?
Multiplying.
Yeah, this reduces to R of S into a single block that is transfer function G1 times transfer function G2. Beautiful. You just reduced cascade form. Parallel form has a pickoff point, R of S, picks off and goes to 2 parallel branches, G1, G2, and the outputs of these are summed. To C of S. Any idea how we would reduce this one?
Would it be like, you wouldn't treat it like it's, like a circuit, right, where you would like add them in a different way?
This is pretty simple. So we have, let's actually follow the signal. If I were to take this R of S, what do I do to it when I hit this G1 block? multiply. So the output of this block is just R times G1. And G2 is what? Or the output of G2 is what?
RG2.
R times G2, which means that C of S is equal to what?
R times G1 plus G2.
R G2. I can factor out my R
You just add them in a block.
plus G2 R. Absolutely. To get this output over input, so C of S over R of S, this is just equal to G1 plus G2. Okay, so this reduces to R into a block that's G1 plus G2. Okay, what we just did, this is called signal following. It's always possible to do signal following, but you have to be meticulous about it to get it right. But once you know these kind of canonical forms, you can look at two blocks that are cascaded and say, oh, I know those reduce because they multiply. Right? I don't have to follow that signal through each one and convince myself every time. Or I can say, I see two blocks in parallel. I know those reduce to being added. I don't need to follow the signal anymore. All right, so let's do an example. Let's do an example where I have a nasty block diagram. I've got R of S, a pickoff point.
What's the third type?
We're going to get to that after this example. I'm going to do an example. Ah, crap. Please come back. Please come back.